Welcome to my channel. Today we are going to be discussing a non-leet code problem. This is an interview Kickstart graph problem called zombie clusters, and I am going to get right into it. There are zombies in Seattle. Some of them know each other directly. Others might know each other transitively through others. For example, if zombies A, B, and B, C know each other directly, then A and C know each other indirectly, and all three belong to one cluster. Knowing which zombies know each other directly, find the number of the zombie clusters. Input is a square matrix where each cell, zombies A, B, indicate whether zombies A knows zombie B directly. Okay, so we got example 1 here in the matrix, and the input and the output is on the right side. So in this case, we have 2 zombie clusters. And this is example 2, where none of these zombies know each other. So that gives us a total number of 5. I've written out the square matrix here. I've drawn out the arrows to show you which of these zombies know each other. In this case, Z0 and Z1 know each other, and we have Z1 and Z2 that know each other as well. Now, it's perfectly possible to solve this problem with DFS. DFS is the most commonly known graph algorithm. It's called depth first search. But in today's video, we're actually not going to be using this. We are instead going to be using the notorious union find. And this is not something you see often. But if you can identify a problem that could be solved with union find, and if you tell your interviewer that you're going to use union find, you will stun him. So I highly recommend understanding how this works. So union find is really all about setting up parents and reassigning these parents to group things together. Right now, what we see here are zombies that are their own parents. This is how it typically works. You set each zombie to point to itself. They are their own parents. They are in their own group. Now, if Z0 and Z1 know each other, we change Z0's parent to point to Z1. And similarly, Z1 and Z2 know each other, so we change their parents to point to Z2. But you should also know that this is totally fine as well. You could say, hey, I want them all to point to Z1. Or you could do something like this, and this should also work. It really, really depends on how you set it up. So for the duration of this video, we're actually going to use this graph that you see here, and I'll show you how it works. So first, we initialize the parents, as we've discussed, and this is the pseudocode that you see to the right, where we have every zombie point to themselves. Now we need to reassign parents if 2 zombies know each other. So in our first iteration, Z1 and Z0 will know each other, so we change Z1's parent to point to Z0. And Z2 knows Z1, so we change Z2's parent to point to Z1. And this is our recursive function, getParent of a zombie. Notice that if we supply Z1 into this function, we get the parent Z0. And if we supply Z2, we also get Z0. And finally, the total number of group clusters. So if you look at this, you'll see a pattern. Those zombies whose parents haven't changed are their own group. Every other zombie is pointing to another group. That's the hack that we use here to calculate the total number of distinct clusters, distinct groups, distinct parents. So here is how we do it. This is the pseudocode to calculate the total distinct clusters, and our answer here is 2. So how do we put all of this together? I'm going to show you the code, and we'll run it. As you guys can see, I have written out the code. I've used Python here, and this is essentially the same as the pseudocode that I'd showed you earlier. and I am going to run this. I'm going to do the full test. Wow, this does take quite some time. All right, so finally, we have finished this problem. It's accepted all the test cases.